So our next talk is by Gerald Rogers from Intel. It's going to be on accelerating network-intensive workloads using the DPDK NetDev.
I don't know. Does it work? Yeah, I guess it does. Okay, good. You have a pointer?
Yeah, there's one right here. You hit this button.
Oh, that button. Okay, good.
And then you can also advances that and backs that.
Advances that, backs that. Okay, good. All right. So, hello. Good afternoon. My name is Gerald Rogers. I am a software architect with Intel Corporation. I'm actually based out of Chandler, Arizona, so we get to enjoy the heat. Lovely down there. I'm going to talk to you about accelerating OVS using the Intel Data Plane Development Kit through the NetDev interface. About 2 years ago, we undertook an effort within Intel to look at OVS from a performance perspective. And at that time, we took an approach to basically kind of fork OVS and create OVDK. It was an open vSwitch development kit. We kind of based it a little bit on top of, we built it on top of Data Plane Development Kit. So we kind of progressed along with that project and got some really great performance out of it. And then about a year ago, we started collaborating with VMware and looking at how we can integrate DPDK into the mainline OVS instead of maintaining a separate fork. And that's been very progressive. I think we've done very good, made some good progress. And at Intel, we've decided that in essence, OVDK would be no longer our focus in terms of development. So we will begin focusing strictly on OVS. And so that's kind of why we're here to, discuss it. So here's our obligatory legal disclaimers. So nice, wonderful Intel legal makes me put that slide in there. I'll let you guys read it off the website some other time. So basically, I want to talk about a reason why we did it, architecture results, and some of the futures. Okay. So what was our motivation? Well, in the data center, OVS as it is, and quite a few workloads would work perfectly fine. Large packets and such, and not a whole lot of interest in performance needed to be increased. However, when you go into other deployment scenarios, like in telco and such, there's a lot of focus on small packets. Okay, and so if you were to look at this particular here, we were looking at a physical-to-physical throughput performance, and all this is 64-byte packets. Okay, well, actually it goes across but you see here on 64-byte, a line rate on a 10 gig is over 14 million packets per second. And OVS within the kernel pushes about 1.1 to 1.3 million, depending on the clock speed. And you see, as we go across, we start to reach line rate on large packets, which is okay, but not for a lot of NFV and various different telco workloads. In addition, you can see here the latencies associated with moving packets through the system. And it's a very high latency, a lot of large cost, which many telco or NFV related workloads are not able to tolerate. And so really basically low packet rate and latency and jitter sensitive workloads are our main driver for this kind of project and why we want to push it. So another obligatory legal slide. All of our performance data we actually base upon a Ivy Bridge or Xeon E5 2680 at 2.8 gigahertz. Again, you can go through this later on yourself, and we do all of our testing with Ixia and multi-socket server class systems. But another slide I have to have in here. So what did we do for the integration into OVS? We decided that unlike DPDK, where we basically recreated the data plane, we would try to plug in with this minimal architectural differences, architectural impact basically into OVS. And so we created a NetDev device that is based upon DPDK, uses the basic DPDK POLMO drivers, which support physical ports and virtual ports for shared memory and vhost interfaces, so user space vhost, which is now a part of DPDK. And then tied directly into the user space switch. Okay, so it's been basically available since March. It's been in the code base since about around March timeframe. It was experimental in 2.3, and then I believe we're still targeted for a 2.4 release within Open vSwitch. So it's sometime next year, based upon the update we heard this morning. In the kernel switch, in this case, is not necessary. It's not used, but it doesn't preclude that you couldn't use it. It still could have both of them in conjunction, but it's not necessary when you're using this. And VMware has done a lot of work to rework the user space switch to make it more performant and more adaptable to this kind of framework. And so you've seen some good performance improvements as a result. It's we consider it a permissive license in user space. So if somebody wanted to fork it and go do their own custom thing, that's fine. We don't care. You can add your own custom enhancement for whatever. So that's the reason why we like to have things up in user space. Currently in mainline Git or patches, the full match and action set of the user space switch, DPDK physical ports, so we can go between physical ports, VM to VM and VM to physical ports, shared memory and DPDK vhost ports, and then also there's been layer 3 tunneling and metering added into the user space. So a little bit more look at the architecture. Basically, here's a user space forwarding agent. Underneath is the NetDev. If you go before DPDK, you originally had tap and socket interfaces. The user space really was more of a development vehicle versus actually forwarding packets. With the addition of DPDK, we basically sit off as another NetDev device, really. The tap and socket still work as they normally would. We don't affect them in any way. VMware has added VXLAN tunnels on the side of the NetDev, allowing you to encapsulate tunnels over any one of these interfaces. And then within DPDK, we provide everything's POLMO drivers, but we provide physical port POLMO drivers, and this basically bypasses the kernel, and so DPDK will take over all of the physical ports and polling and operation. And then also IV shared mem, a shared memory interface into a QEMU or a KVM, as well as a vhost, user space vhost into KVM as well. So that's the general architecture. So what do we got? So with the DPDK, this is physical ports. You see here that we now push up to nearly line rate. This is all single core performance versus what with the kernel was about 1.3 million packets per second of throughput. And you see the big change in latencies associated with going to DPDK. We dropped down to, it's about a 50x improvement in latency from somewhere close to 3,000 down to about 30 microseconds of latency through the system on physical ports. So that's kind of basically the improvement that we've introduced with the user space switch. Sure, go ahead.
Sorry to interrupt you. Those latencies are for what flow tables? Do you have anything in your flow tables here?
Trying to remember how many we put in there. I think this was for 10,000 flows.
Does that do what?
They're basically just random flows that you know do look up on various different packets and forward them out. I don't remember the exact configuration off the top of my head.
Okay, it's just output, all right?
Yeah, it's just output. So this is basically just forwarding between physical ports, right? Yeah. In this case, these are static, so we went through OFCTL and basically programmed out the flows directly versus allow the controller to do the work. Yeah. Okay. Let's see where else. Okay. So futures, as a result of moving into user space, we lose, we're bypassing the kernel, which means we kind of lose some of the kernel functionality. And so kind of some of the things that we're asking, we're trying to conclude with ourselves is the bifurcated driver, which is a driver that we're introducing within DPDK. Using that would allow both user space and kernel paths simultaneously. And so you could use hardware classification to put frames in either the kernel or into the user space. And so the other part is, what are the other major gaps? So a couple of them that we see are user space packet filtering, introducing the ability to work for security, ACLs, NAT, or deep packet inspection to happen within the user space, as well as user space connection tracker to allow the similar type of functionality that was introduced today within the kernel, but in user space. They don't necessarily have to be part of OVS or part of the user space switch, but a mechanism that would allow them to be integrated with the switch, or such. And our desire to see user space become a first-class data plane, right? Okay. So a little bit on the bifurcated driver. With the bifurcated driver, we allow the hardware classification. So if you look at our NICs, Fortville, Niantic, they incorporate flow director or flow classification and redirection within the NIC. So by using that capability, we can actually force different flows onto different queues within the device. This allows us to go up through the kernel driver, or we can bypass the kernel completely and go up into the DPDK NetDev level. Now, what this allows is you to, if there's a particular feature that you would like to go through the kernel to get, and you can use the OVS kernel driver, OVS kernel implementation to implement that feature. And then also you can, if you need a high performance path, then you can bypass the kernel completely and go straight up into DPDK NetDev. So, okay. Got a question way up at the back.
Hi, I'm Chandra from AVI Networks. Can you comment on the CPU utilization, especially when you are doing the poll mode drivers and when you wanted to poll the packets?
Right. So DPDK by default will consume 100% of a CPU for each interface that's assigned to poll. So if I go back, just a minute, I don't know how far I can go back. So right now in this data, we're only showing a single core used, right? And this is actually true for both kernel and DPDK implementations. So we're showing this throughput for one core. Now, in the smaller packets, of course, the whole core is basically consumed to accomplish that kind of array. But as you go through into smaller packets, we don't really consume a full core from the perspective of moving packets. But due to the pole mold driver, we will use up a whole core. And there are some techniques that we've introduced in DPDK to kind of alleviate that. And so it becomes a trade-off between raw performance versus slightly lower performance, but lower CPU utilization. And we basically can introduce sleep states in the processing of packets, which will reduce the amount of CPU utilization that's used. So there are techniques, but it's the real advantage of DPDK is that it is really in the pole mode drivers. The latencies with interrupts can be pretty high, and so by switching to a pole mode driver, you get the best performance. So, okay. Back up here again. Where was I? Oh, here we go. Sorry. Okay. So basically, that was the bifurcated driver. This is actually right now. I think it's patches on the kernel right now. So we'll actually go into the Linux kernel, or at least it's being pushed to go into the Linux kernel. And so you'll be able to use this feature hopefully soon. Okay. So our desirable augmentation of the data plane is really to, oh, darn it, sorry, push the wrong button. So our basically is to introduce into the forwarding path the packet filter and connection tracking type of structures, operations. And again, we're not really stating that it should be a strict part of OVS, but a mechanism to interface into the user space forwarding plane to facilitate these features. Okay. So let's see this one. Oh, is there a question? Oh, it's up to you. I don't care. Anytime. Okay, yeah. So basically, in summary, the DPDK NetDev greatly increases our packet receive rates, and well, basically packet forwarding rates, not just receive. So it bypasses the kernel, meaning that there is going to be loss of some functionality until it's put into user space. And it's time basically to consider putting high performance packet processing in the user space. The benefits are there. With some additional work, we can get better scaling across multiple cores. And we can use the bifurcated driver to facilitate both fast lane as well as every kernel feature, if you so desire. And long-term approaches to move more functionality into user space. So we're seeking feedback, code, and additional benchmark tests as appreciated. Okay, that's it. Questions?
Hi, Luigi Vizzo, Università di Pisa. I'm very interested in the part that communicates with the virtual machine. So you have presented two different APIs. Can you comment on the differences, performance, etc.?
Right. So there's two primary methods today: IV shared mem and vhost. Shared memory actually builds upon, QEMU has a device called shared mem, actually, is what it's called. And we kind of piggyback on that device. Now, we've actually introduced a patch that's not mainstream or not upstream in order to use this. And what we do is, see, DPDK operates off of huge pages. So we go and we allocate huge pages from the kernel, and then DPDK takes them over and just chunks them up however they need them. We map those huge pages through into the guest. And what that allows you to do is basically a zero copy in between a DPDK application in the guest and the DPDK application on the host. So it's a very fast interface. There's no copies or anything associated with this interface. vhost is a little bit trickier in the sense that it still uses the standard VirtIO vhost interface. So when you launch a KVM or QEMU guest, You'll have a VirtIO driver on top of it, and then you have vhost that exists in user space. Now, we do some functionality inside of DPDK to basically snoop the creation of the backend RX and TX queues on the vhost. So when it gets created, we'll pull those queues out, and then we map them up into DPDK user space. And then we actually do, there is copies between that have to occur in order to put the packets into the guest. So I don't have performance data right now on this, but we do have on OVDK, this is kind of new for OVS, user space switch. But we do have performance data on OVDK that probably likely will be very similar to it.
But is one of the two mechanisms preferred to the other, or why do you have two?
Well, so it depends on your deployment environment, right? If you're in a trusted environment, like an appliance, for instance, right? In other words, if you're a checkpoint or somebody like that where you control the whole thing and that you control what virtual machines are on there, you're going to go for the fastest interface, right?
Which is
which is going to be the shared memory model, right? But if you're not in a trusted environment or you don't trust the virtual machine, you're going to go with this one because there's copies involved, and so you're definitely copying between address spaces, and it's going to be secure.
Okay, thank you. If I may, one more question. How do you handle the notification, the VM exits or interrupts?
Motivation?
Notifications between...
Oh, sorry. You mean between the VMs?
Between the VM and the user space DPDK.
Right.
There, I guess, you have the IRC.
Yeah, so from the vhost perspective, we're also listening on the event channel, the vhost event channel. So we can introduce, so we are listening on for all the different vhost messages. And in the case of a packet, like, so sometimes you have to interject a soft interrupt, that we do as well. Okay. Now, if you're running it, we also have DPDK can run on VirtIO as well, right? And if you're running the DPDK with VirtIO driver in the guest, then that soft interrupt you turn off. And we actually get better performance when you do that. So.
And what about the shared memory thing? I mean, I can take this offline if I'm boring people. Let's leave room for someone else.
There's another talk tomorrow, but in particular on the virtual interfaces. Yeah.
Chris Wright, Red Hat. First, thank you for admitting that OVDK doesn't exist, and thank you again for working upstream with the OVS team to merge your code. I'm deeply skeptical of your final slide saying that the right choice is to move all of this functionality out of the kernel and into user space, and I think you'll find your performance benefits waning as you move more and more functionality into user space. I understand the value of polling, and we could certainly consider other alternatives in the kernel to do accelerated receive out of a DMA buffer into an application. Do you really think that the right answer here is moving all of the Linux kernel networking stack into user space? I know that's your summary, but thank you.
Well, I wouldn't say it as my summary if I didn't. Yeah.
All right. So thanks again for admitting that OVDK is dead and working with the OVS community. I really think you're moving down a dangerous path, and I would like to. I'm a broken record here, but I would.
Yeah, I know.
I'd like to say that I'm deeply skeptical of this long-term effort.
Thomas Graf, Nuara.
Thomas?
First of all, thanks a lot. I saw, or the question is, what is your plan regarding vhost user, which has been developed in the context of SnapSwitch? And I think it was proposed for DPDK as well at some point, but didn't seem to have received a lot of traction. Any plan to support vhost user as replacement for the current vhostnet approach for the vhost vport?
So you're referring to vhostnet inside of KVM?
No, I'm referring to the vhost vport, which is currently requires you to remove the def vhostnet device versus using a complete user space based vhost implementation that SnapSwitch that has been developed in the context of SnapSwitch?
Right. Yeah. So there's some work going on in QEMU, right, to replace to a live user vhost, if I remember correctly. And we are looking to take DPDK and move it to that model. And that should simplify a lot of the issues with having to use queues and fuse to interact with the backend vhost in the kernel.
Okay, that's great to hear. I would definitely like to talk to you about moving to vhost. I think that's the right
So
thing to do.
our goal is to try to move to upstream, and some of the work that's going in upstream is going to make this a lot easier and cleaner than what it is today.
Awesome, thanks a lot.
Hi, Madhu Chhala, Neuro Networks. So I kind of love DPDK, for its performance and everything. But when it comes to like debuggability, I find it like problematic because there are things that are not exported anymore. Like for instance, like all the e-tool stats, which I'm used to like seeing with normal NICs, normal Linux interfaces. I don't see them with DPDK, or even like using TCP dump to actually like look at packets and figure out, basically figuring out like what's going wrong. So is there any plan to like support e-tool like stats and say TCP dump while at the same time we're using DPDK with OVS?
Well, so from the stats perspective, that's a regular request we do have. I would actually have to go back and check with the DPDK team and see if that's actually on the roadmap. I don't honestly know where that would fit in the DPDK roadmap.
Okay.
It's a different team, but yeah.
Okay, thank you.
And TCP dump, well, right now we basically consider that as a customer application, but it's something that could be added in.
So basically we would be running a TCP dump DPDK app in addition to like OVS and basically. All right, thanks.
Just following up, so you don't have like libpcap that's compatible with DPDK yet, is what you're saying? Or?
Oh, actually, I think PCAP is available, yeah.
So TCP dump should work then, presumably.
Yeah, that's right. Yeah, PCAP is actually a valid pull mode driver now inside DPDK, but it's a little bit different because we're expecting for the PCAP interface to actually use the kernel, right? Like you're interfacing to a kernel, to the kernel itself. So, not the.
So I had one question about the sort of OVS integration. Does this mean, and perhaps for Ben as well, does this mean that a future version of OVS, I just install it and I'll get the DPDK version for free without having to do anything? Or if I apt-get install it? Or what's the, maybe this is deployment as well, like, is it sort of a no-brainer as the user that I'll just see these things magically, or are there special things that I have to do, special hoops that I have to jump through to enable it?
That's actually a question for VMware, not me. I think.
So a single OVS binary can support both kernel-based and DPDK-based switches. There are a few extra hoops you have to jump through if you want to configure it using DPDK, but as long as you build against DPDK, you have the option of using it at runtime.
I guess that didn't entirely answer the question. So does this mean that the packages, like if I get vendor packages from like Ubuntu or Fedora or whatever, that it'll just install it and I can just run it, or do I have to build it myself?
I don't know what all the vendors are building.
I think you have to build it yourself because right now the DPDK doesn't have a standard API or a lockdown API, so it's going to vary depending on the version, right? So I think for the time being anyway, you would need to take your OVS source code and compile it against DPDK.
And then my last question is that it looks like the main focus is looking at sort of PHY to PHY performance and VM to VM performance. Does DPDK help at all with, say, container to container performance of Open vSwitch?
At the moment, no. But as what we've done with VirtIO and vhost, we're looking at similar type of work for vETH within the container. I just know I just know that they're looking at it. I don't know any timelines or anything like that, but it's being investigated.
So one of the issues that we see with the DPDK is with the poll mode drivers is especially in the transmit path where we have to do the doorbells, and most of the time it results in the VM exits and cause significant issues in performance. Are there any plans or any other suggestions that you have to alleviate some of those problems? Is it like hypervisor specific, or don't you see that kind of problems when you bring DPDK to the OVS at the host level?
If you're seeing VM exits from a pole mode driver perspective, then you would be running DPDK in the guest. And is that, we can take this offline. I think it's best question that we answer offline. I'll be back here tomorrow if you're here. I unfortunately have to leave after this talk, but.
Hi, Alex from OVS team. Thanks for the speech. I'm curious, how mature do you think the current DPDK library is? I think the latest one is 1.7.1. Another question is there any new major changes on the roadmap of future DPDK library releases? Thanks.
Yeah, so 1.71 is the latest, and it's pretty much locked down. It's not going to change, but DPDK roadmap. Honestly, I don't know exactly how to answer that one. We have a full roadmap that goes out to into next year, but I don't have that with me on this particular slide. And there are a lot of features we look to add in, and of course, customers in industry comes and tells us basically what they would like to see, and we put them on priorities and add them in. Is it on dpdk.org? I'm not sure. Yeah, it's on dpdk.org. On the announce is some, yeah.
This is Flav from Red Hat. Speaking about the integration with OVS, can you comment about hardware offloading?
There's another discussion that will happen tomorrow where they're specifically covering hardware offload. That'll be Dan Daly, Uri Elzer. We'll discuss that.
Frank from Cosmos. Yeah. So is it production ready? Is it?
I believe it's close, yeah. There's, of course, some of the features that are key to some customers are not there, but it is reasonably stable at this point. So, okay, we're way over, I think. Oh, one more, okay.
Thomas Graf, Nora.
Yeah.
Maybe more of a statement than a question. I think regarding context of production ready, I think what would be really helpful and needed is what Justin just mentioned, which is stable APIs for DPDK. I think otherwise we will not get to a point where it gets consumable for a larger set of use cases.
Yep, no, I understand. I fully agree. We recognize that as an outstanding issue with DPDK, and it is something that is being investigated is to stabilize the API. So.
All right, thanks a lot. Let's all thank our speaker.